Hello. So can we start the meeting? So the seminar? Okay. So I'm glad to introduce you Ricardo Gafeira, who is here. He's a young scientist. He did the PhD, the physics degree at the University of Coimbra, and the master degree also there in the University of Coimbra in Portugal. He was there, I think, about 3 years working in the university in different projects. And after that, he moved to the Max Planck Research Institute in Göttingen to do the PhD. So, and he defended his PhD 1 year ago in January. So he's really a very young doctor. So, and then after that, we hired him here in the solar physics group from the Instituto de Astrofísica. And I want to welcome him to the Institute. And it is his first seminar here, so I hope he can do it very well, so we can have a very good impression. And he will talk today about what he did mainly during his PhD degree. So he's going to talk about the slender calcium 2H fibrils observed with the sunrise SUFI instruments. It's a mission where we are in this institute very deep involved. And he will also comment some of the plans that he has for his postdoc here at the institute. So welcome, and please take your time and enjoy.
Thanks, David, for the introduction. Thanks, everyone, to see my talk. This talk, as David mentioned, I will present the results or the work that I did during my PhD with some collaborators that was mainly focused on these calcium 2H fibrils that we observe with the sunrise mission. So here on your right side, you see already, sorry for the lack of contrast, you see these elongated structures that was the main topic of my PhD. I will start to introduce very briefly the solar atmosphere. The sun is separated in several layers that are the separation is based on their average physical properties. So we have the nucleus, the radiative zone and convective zone that is part of the internal structure of the sun. But we as a solar physicist, you are looking always to the solar atmosphere, and this solar atmosphere that I will introduce here a little bit more in detail, even though just I will show you the average properties of it. You can see here on the left side on this cartoon that the sun is separated in 3 main regions. That is the photosphere, that is the surface of the sun. When you look to the sun, is this circle that you see, the yellow circle in the sky. That is around 6,000 kelvins, and then higher up is the chromosphere, and then you see here already that you kind of separated between the 2 layers, the lower chromosphere and the upper chromosphere. And this is a very, very thin layer that you can see here on the right side on this plot, where I plot the height and the temperature and also the density. And you see here already that the chromosphere is very, very thin. It's still 1.5 megameters, but for the scale of the sun, is a very, very thin layer. And a lot of things are going on there. And as you see here, at the beginning of the chromosphere, the density it's quite high, and then it decreases very rapidly. And till we reach what we call transition region, that is a very, very interesting layer when we have this very high increase in temperature. And after this, we have the corona. That is, here I show just an average value of 1 million kelvins, but you can reach several million kelvins. And our study, we will focus mainly on the chromosphere. It's where we think that the slender calcium 2H fibrils are rooted. And here I will increase a bit more this cartoon, and I will show you here, I don't know if you can see it here, this is the surface of the sun, that's called the photosphere, and then you see here this small layer of plasma above, and here you see a lot of structures going on, very high dynamic structures, a huge range of temperature, and this reason is very important because we think that what happened here can cause, for example, one of the biggest open questions in the sun, that is the heating of the corona. And we think that what's happened here can give us answers of what happened above. Because if you have a warm body, you don't expect that the temperature, as I showed here, rise so rapidly. And we think that what happened in chromosphere due to the magnetic fields or some dynamics of the plasma can hit the corona. And here I enhance again the small details of the chromosphere that is very, very thin. The 1.5 megameters is very, very dynamic. We have a huge range of dynamic scales. The temperature range from 4,000 kelvins to 10,000 kelvins. The plasma density drops 4 orders of magnitude in a very, very short range. And here we say that the plasma beta is very low, means that is basically magnetic field driven. So the magnetic field plays the most important role in the dynamics. And with the new telescopes, with a very high resolution telescope, you see all the structures there in a very, very high detail. Here I just show you 2 examples that we call spicules that we see off limb, basically outside of this circle in the sun. And you see here on this plot, basically each one of these rectangles, it's one snapshot, so the time goes in this direction, this is height. And you see here that these linear structures start to develop and grows and then start to fade away until they disappear completely. This is what we call spicules. Some recent works, they even describe the existence of 2 types of spicules, that are type 1 and type 2. One grows in a parabolic way, or like a ballistic shooting, and then it grows up and then decrease, and the other ones, they grow and then they fade away with time. And you see here they are around 6-7 megameters. On another scale, and on the disk of the sun, you see, for example, fibrils, but other type of fibrils. You see here on this image, this is a H-alpha image that is looking inside of active region, and you see a lot of these filaments. You see dark, you see bright filaments, some are absorption, some are emission in H-alpha. But these are much, much bigger than the ones I'm talking about. And part of our work is to compare all these structures to the structures that we are looking at. And to give you an overview what can happen there and the structures that we want to compare, you see here 4 different examples of these structures. The name of these structures varies a lot, depend also on the authors. Some authors call some different names, but this is my summary of the structures. So one of them is called moctals. They are much bigger than the fibrils that I want to talk next. They are from 1 to 10 megameters. They are usually rooted on the edge of supergranules. Supergranules are huge convective cells on the surface of the sun that concentrate the magnetic field on their edges. Don't confuse the supergranules with the granules that we see on the surface of the sun. These are much larger structures. And these structures, you can see them H-alpha and calcium-2. The other category of these structures is fibrils, where we think our one fits, but a much smaller scale. They have few hundreds of kilometers to 15 megameters. They are still long, some of them. They are very, very thin. Some of them are very few hundreds of kilometers, and they are kind of short-lived. And usually they appear close to active regions, to sunspots, splash, or some other structures. An interesting structure that they appear that can be kind of correlated with the structure that we want to show is the RBEs, or rapid blue shifts, that is very, very fast events that we see in H-alpha and calcium infrared. And they are very, very short-lived, less than a minute, but they are very, very dynamic and very, very fast, shifting in one wing of the line. And finally, as I told you, the spicules, they have 2 types of spicules, and they are the closest ones in terms of morphological properties to the fibrils that we are observing, but we still don't find a clear relationship between these spicules and our fibrils. And then we can kind of summarize all these structures on this cartoon. On this cartoon, we show the surface of the sun here. They see the granulation that I told before, and the supergranulation that concentrates magnetic field on this network regions, and you see here these black lines, they represent the magnetic field coming out of these networks. That calls what called the canopy, and you see here already that this author put some of the fibrils right on top on these magnetic flux tubes. We can also call to these, and I will call from now on to these magnetic field lines, magnetic flux tubes as approximation. And you see that these fibrils are rooted there. But we think that this fibril is just a category of them, because you see here already that a lot of magnetic field, weaker magnetic field that come from the granules, can also create all these canopy structures. And you see a lot of things going on here, some wave conversions. You can even see already here the spicules that appear in some other location. But the relation between all of these structures is still a bit unclear. Some of them you have indications how they relate with each other. Some of them are completely independent. But one of the goals to study the chromosphere is to see how they relate with each other, where the structures are really rooted, and analyze in more detail the dynamics. For this, to analyze it in more detail, the chromosphere, we use the Sunrise Observatory. And here I highlight the Sunrise Observatory because it was the first time, from my knowledge, that we were able to observe chromospheric structure with such high resolution that for such long period of time with a very, very high quality data. And the Sunrise Observatory, it's a balloon, a stratospheric balloon with a 1 meter Gregory telescope, as you see here on this image, that flows around 37 kilometers. Why at this height? Because at this height we expect a very low UV absorption, also almost seeing free conditions. And it flew already 2 times. The first time we observed mainly quiet sun regions, or quiet sun because it was during a minimum, but on the second flight, that's with the data that I will show you next, we use the data from second flight from 12th of June. And 12th and 13th of June. And it flew for 6 days, but we are just using 1 hour of data. This hour of data was acquired with the 2 scientific instruments. One is a SUFI, that is a filter graph. Basically, you have a narrow filter or broad filter, and then you collect the image that the instrument collects. And is a field of view of 15 by 39 and resolution of 0.37 arc seconds. The other instrument is the IMAX, is a magnetograph that was developed with a strong collaboration from the EAA. And here you can extract the intensity of the image and also the polarimetric information of the light. And this allows you for more detailed studies in magnetic field and so on. But this I will talk a little bit later. Now I will show you the data set and describe it a little bit more. So we use the calcium 2H data that you guessed already that we are going to use, taken by SUFI. This was the field of view. So this is the global image of the sun, of the full disk, and we are looking to this active region, 11768. And this is an approximation of the SUFI field of view. So we are looking here, very close to this active region between these 2 different polarities regions, as you see here on your right hand side. This small rectangle is the SUFI field of view, the big square is the IMAX field of view, and the black and white regions indicate opposite polarities. So we expect that you have a lot of magnetic field lines connecting these 2 opposite polarity regions. Also, I don't know if you can see, you have a lot of small magnetic field concentrations here, so you also expect to have a lot of small magnetic field connections between these 2 regions. And we have 1 hour of data of this region continuously with 7 seconds cadence, and the filter that we use is 1.1 angstrom. That is already quite narrow for this type of studies. And on these studies we use the typical level 2 data, that is just flat fielding, phase diversity, and arc current correction, but we also use what's called MONFPD, that is an image restoration technique that allows us to extract the best possible image out of the telescope, inferring the wavefront deformation that we face. And to understand a little bit more what we can see on this data set, I want to introduce you the formation height of calcium 2H. When you look to this image, they look in 2D, and you can probably think that you are looking to the same for the same geometrical height. But this is not true. Here on this plot, this comes from a simulation performed by Mark Carlson. You see the x on the horizontal axis, and here is the geometrical height. And you see here a lot of different lines, but the most interesting line for us is the solid blue line, that is the line represented here, that represents the load tau equals 1 for the calcium 2H emission. This shows basically where, in a rough estimation, the light came from. So when you look to this data, you are not looking for a perfectly constant surface, but you look for some variations in the surface. And this can complicate a little bit the interpretation, because you never know exactly the geometrical height that you are looking at. And if I run this movie, you see how this line changes with time. And you see here that the variations are very, very high. In addition to this, we have to convolve the emission of the line with our filter that I showed here on the right side. So all these lines are the synthetic data for calcium 2H for different types of atmospheres. When you look to the quiet sand, close to a plage or active region. And you see here that is characterized by a strong absorption. But in the line core, you have two peaks of emission. That is the bright structures that we see that result on these two peaks of emission. And here on this dashed line is our 1.1 angstrom filter. So we need to convolve the emission of this line with the filter to see the region, or try to infer the region that you're looking at. In addition to this, we know that, imagine that we have a flat spectra, and the line is absorbing the spectra. And if you look to the radiative equations, you can say that this region here comes for deeper layers, that where we have more, the radiation field is stronger. And then as you go down on the wing of the line, you start to observe the higher layers until you reach the line core that probes the highest layers possible. With this, we can say that our filter will not probe such high layers as I showed here on this simulation with a almost infinite resolution, but will probe a little bit deeper layers. And here I will show you our estimation of the geometrical height that you are looking at. Please take in mind that this is an average, a very, very rough average, and we think that most of the information that we are looking at will come from this, what I showed you before, low chromosphere, and this is around 600, 700 kilometers. And here it is right on top of this very small scale canopy. That means that this region is full of small flux tubes that look like arcs, but is also full of some magnetic field sheets, so we still don't know exactly each magnetic field lines our fibrils are probing, and I will show you later a little bit more into detail. And show you something more interesting or nicer, I will show you here the actual data. So on the left side, just for context, I'm showing you the continuum image that is, as I said, the deepest layers of the the atmosphere, in that case the photosphere. You see here the granulation that I talked before. You see here a pore that represents very, very high magnetic field concentrations, but also a very, very a lower temperature. On the second panel, you see the actual calcium 2H data, and you see that it's very, very, very dynamic. So each frame is 7 seconds, and you see here already a lot of these elongated structures moving all the time. You have here also a small flare, and here is not very clear, but you have a lot of these fibrils that they appear, they cross. You have very long ones, and this complicates a lot the detection and tracking of these fibrils. And at the beginning, we started to do a manual detection, but it was very slow, and we were not evolving too much. And then we developed automatic code to extract these bright elongated structures. And on the third panel, the panel C, you see here the result of this extraction. So each one of these white structure is what we think is elongated structure. But due to the fact that they cross a lot with some other structures, we need to exclude a lot of them. And then on the right side, on the panel D, you see our first exclusion of the data, that is very, very small scale structures. If they look like spherical, we exclude them. And if they look very, very regular, you also exclude them. And this is what we, at first, consider a fibril. But still, this is just a single fibril. So for our study, it's interesting, but it was not our goal. So we apply a second criteria, that is, we need to identify this fibril in the same location 5 out of 6 frames. And this will allow us, first, to be sure that we are looking to the same fibril, or we think that is reasonable enough, and give us the tracking information of the fibril. So basically, we take one of these structures, we overplot them, and if part of this structure will appear in the same location 5 of 6 frames, we say, okay, this is one fibril, and I will analyze it. And here on the right side, you see the evolution of this fibril. So this panel, each one of these panels, it's one frame, and then you see the fibril here evolving in time. You have already some bright variation, then it gets elongated, and here is the detection output. That is the backbone of the fibril, that is the single line reduction of the structure, and then we smooth it. So it's this dark line here that is represent the core of the fibril, I would say, and this is our first estimation of the width and the elongation of the fibril. And you see here already, it's more clear to see it here, how the fibril evolves. Here it is more or less linear. Here you see already a small kink, and also the length variations of the fibril. This is a very, very short-lived one, but to be easier to see, we plot this one here. And the first morphological property that we can extract out of this method is the lifetime. And here you see the lifetime in seconds. This is the normalized frequency of occurrence. And the first thing that I want to point out is this gap here. So since we needed to look to the same fibril in 5 frames out of 6, we always have a limit of 35 seconds. So this doesn't mean that the fibrils don't exist. It's our method will automatically exclude all of these fibrils. And this is the distribution that we got. So we have a decay rate of 10 to minus 3, and this is exponential decay. So you see that most of the fibrils are very, very short-lived, less than a minute or so, but we have very, very long-lived ones. But we also need to take into account if you have a very long-lived fibril, it's more difficult to detect it because of all the crossing fibrils, and then at some point it's difficult to be sure that this fibril is the same, or there is another fibril that goes cross to it, and it's difficult to be sure that it's the same structure. But of course, this is also dependent on the method, and we also try a different approach for the lifetime of these fibrils. That we took the third panel that I showed you on the movie, and then we took the position, the fibrils along this virtual slit, and plotted over time. And that's what I show here on this plot. So this is time again. This is the arc seconds. It is a position along this red virtual slit here. And then we relax our criteria. Before it was 5 out of 6 frames, and now we have 2 out of 16 frames. And if you look at this plot, you can see the position of the fibrils that are represented here by these blue regions or blue patches. And you see that the fibrils, they tend to appear, as I showed here in this red part, almost in the same location. So they appear and then they disappear. In our first method, basically, each one of these small patches, if they just have one gap in between them, was a fibril. But for example, here between these fibrils and this one was a completely different structure. But here we see that they follow a trend. It seems that the fibril, it's there, it appears, it's being heated or cooled down for some physical process, but the structure that supports it, it's there. It seems that it's much longer because you see it here, you see it here, here, and also here. And when we compute using this limit, the lifetime of these structures, and this is the extended lifetime tracking, and that I showed here. So you still have, again, the 35 seconds gap that is induced by our method, but the distribution looks much, much different. So now is a log normal distribution with a mean of 446 seconds, and they are much, much longer lived, like 3 times longer. We also fitted the same distribution with exponential decay, and you see that the exponential decay is much, much slower than the previous decay, the previous distribution. At this point, we thought that it could be the detection that was wrong, but then we kind of made a comparison or a blind test between the automatic detection, our manual detection. And even with manual detection, we were excluding the fibrils on these gaps. So we are sure that the fibril is really disappearing. It's not just the tracking method that is missing. Of course, it can be missed some, but we are reasonably sure that it will detect the fibrils as we expected. The next morphological property that we infer is the fibril width, and here I will show you just one example. So imagine that this is the fibril. This is the same image that I showed you before. So that's the fibril, and that is the backbone of the fibril. Then you put a virtual slit in the center of the fibril, perpendicular to the backbone, and we plot the intensity that we see here. This is the position along this virtual slit in kilometers, and this is the normalized intensity to the quiet sun. So it's the red line that you see here. And then to extract the width, we fit this distribution to a Gaussian plus a linear background. And this linear background is important because it allows us to constrain the quality of this fitting. Because these fibrils, they are elongated structures, but they are also optically thin. So what's happening below or above also contributes for the intensity. So imagine that you have a fibril or a filament with certain width, and then below we have some other structure that is a little bit offset. So you have a very strong asymmetry on this profile. And if you just fit it with a Gaussian, we will be a much, much broader distribution. Of course, it could be very, very broad, and then we'll give a bad fit, but you notice that in some of the cases we were getting good fits, even though the linear background was completely off. So we apply a constraint to this linear background. If the slope was higher than a certain value, we exclude this from our distribution. Means that was something going on up or above, and then or down or above, and then we exclude it. And this is what we got for the width distribution. So you see here the full width of maximum of the Gaussian that we fit, and the mean of this full width of Gaussian is 182 kilometers. So these are thin, but not so thin that we expected at the beginning, but could also be a difference between the method of extracting width. And some other studies, they show that they are a little bit more thinner, but they can be also different structures seen in different locations. So, but you see here that some of the fibrils, they are quite close to the diffraction minute of the telescope, that is a little bit below 100 kilometers of the data, and then they have this very symmetric distribution with 182 kilometers. That is, comparing to some of the other structures that I showed you before, they are very, very thin. But we also want to look in a more general view to these fibrils and how they evolve in time, and we want to condensate to in a more reasonable plot. And then we introduce what we call average backbone. And the average backbone is computed that way. So we take for each fibril the backbone in time that is represented here by its black line. So this is just image position in pixels. And then we fit a second order polynomial to all these black lines, basically to all these single backbones. And we got this red line that we call the average backbone. Here you notice that we extended a little bit more than the limits of the previous backbones, because if you remember, our backbone was a single line reduction of this bright structure, but if you reduce the structures to a single line, you also miss the edges because you reduce it, and it's how the method works. So we needed to extend basically the width estimation that we got from the previous work. And this allows us to infer the maximum length of the fibril, hoping that this fibril will probe the maximum that we think this magnetic structure or the structure that probes the fibril. Also, this approximation allows us to construct this mesh, and this mesh will be very useful to infer the intensity of the fibril and their evolution. And I will show you next how we use this mesh to destretch the fibril and show in a very clean way the evolution of the fibril in time. The length that we got from this distribution, from this method, I show it here. So you have length in megameters, and then this normalized frequency of occurrence again. And then you see that they are very, very small, 1.38 megameters. is in order of magnitude of the granules. So it can be indication that the structures, they are kind of related with granules, but we also need to think that they are higher up, so it can be just some mechanism create these fibrils and then they are rooted much far away. So we cannot give one-to-one relation between this and the structure that I showed you before, these small-scale canopies that they were created by granules. But still, though, they show much higher structures. And to finalize this part of the morphological properties, I will compare, as I told you from the beginning, that was one of our goals, the CFCs, that is the slender calcium to H fibrils, that is this work with some other structures that we think are the closest ones to them. And you see that the lifetime is very similar to the spicules, but even though the width and the length don't match so well, so we don't know if this is just a projection effect because the spicules are off limb and we are seeing on limb, or also a fact that we are looking to deeper layers or higher layers, and this can create different structures that, since the structures tend to expand in height. And here we compare with the calcium to CaiiH fibrils, that is another calcium line, but here we just have one snapshot published by Ana Priatralia, and here you see that the width, they kind of match, but we don't have lifetime information still for these kind of structures. And the length, they tend to fit. But this also, since we just have one snapshot, it's difficult to see if this was a local phenomena or some global behavior. And passing for just these morphological properties to the intensity analysis of the fibrils, so we use this match that I showed before to interpolate it in a linear way. So basically we destretch the fibril, and then I show here on this plot, each one of these rectangles show one snapshot of the fibril, so this is the position along this average backbone, normalized to 1, and time goes in this direction. You see it is a reasonable long-lived fibril, and you see here that the intensity starts to grow from the center to the edges, and this is the most common case. You can imagine that this can be a loop. Imagine that you have a flux tube that is a loop that is rising and then is being heated by some mechanism from the center to the edges. And then as it grows, it starts to cool down or being heated on the edges, and it starts to fade away. But some of them, a quite significant number of them, 25%, it shows completely the opposite. The brightening starts on the edges and starts to propagate to the center. If you have this of flux tube growing up, this model will not fit here. So we still don't know exactly the magnetic field configuration of these fibrils and the exact heating mechanism, because if you think in one for one type of brightness variation, the other one will not fit so well. Or we are thinking wrong in our possible brightness variation. It can be compression, radiation coming from other places, or they even show different type of magnetic field structures supporting it. But we are still looking for this, but there are indications that they are loop-like structures. There is a paper published by CaiiH when he correlates the location of these fibrils with a magnetic field extrapolation, and a significant number of them, they show a strong relation between these magnetic field loops, but it's still difficult to explain, to give one explanation for the two types of structures. But as I told you, we assume that they are magnetic flux tubes. And if they are magnetic flux tubes, you expect to observe MHD waves on these tubes. And here I show just briefly the three types of waves that we can observe on these structures. The first one is sausage mode, that the tube works like this. It compress, expand the time, and they are excited mainly by compression. You have the kink waves, that basically is something giving a kink to the flux tube, and then it creates this perturbation, and then the magnetic field as a restoring force restore it again. You need to think that this is a magnetic field environment, so you have magnetic field, you have the electrostatic pressure, but also the magnetic field tension also plays a role as a restoring force. And the last type of waves is the Alphen wave, that is a torsional force that we don't expect to observe because it's not It's not a compressible wave, so we don't expect to have intensity variations in our fibrils, so we didn't try to find them on our data. And the observation of these waves in our fibrils is very important because it can give us hints of the magnetic field, if they are present or not, the energy budget, and possible dissipation. So you can say that this wave has some energy, and if their energy we can dissipate to the environment, and in the end, hopefully or not, eating the corona. As I told at the beginning, it was one of the most open questions in solar physics, and in the end, what excites these waves. And here I showed you exactly the same plot that I showed you before. The fibrils stretch, the time goes in this direction, and this is the length now in kilometers. And we compute the width of the fibril with the same method that I described before, and you also compute the maximum intensity along all these virtual slits that they vary between 20 and 80% of the fibril. And then we use the information of the intensity and width to compute the sausage mode oscillation, for example. For this, we use the wavelength analysis that allow us to extract the phase diversity and the period of oscillations. And here I show you the period on width and intensity, and these 2D histogram. And you see that there is strong correlations. Remember, the zero is not here. This we start a little bit higher up to be possible, to be easier to see. But you see that there is a very strong relation, or close to one-to-one relation between width and intensity. And if you recall this plot or this cartoon, imagine that we have a flux tube that is being compressed. So we have the plasma being compressed, and since it's also optically thin, you expect that along your line of sight on this resolution element, you have an enhancement in intensity. So when the fibril is compressed, you show higher intensity. When it is expanded, you show lower intensity. But for this, we need to have opposite propagation phase. And this we can see here. So we compare the phase difference between the two types of oscillations that is showed here on this histogram, and you see that most of the fibrils, they show opposite phase between the two intensities. That is, kind of validates our model, that we have something compressing, getting more intense, and then when you expand, it gets thinner. And this can be visible also here. So we took the intensity and width for some one specific virtual slit position, and then time goes in this direction, and then this is the intensity, and then we see here that as the width grows, the intensity decreases, and then the width, and then this behavior, it's very, very clear. And this is an indication of sausage mode. And if you compare the possible sound speed and Alpha speed in the medium, that sound speed is around 7 kilometers a second, and the Alpha speed can vary from 7 to 25. We can claim that this is what we call fast sausage mode, because all the phase speed of the perturbation is always higher, almost twice the size, with a quite strong error bar, but is reasonable enough to say that we are present on sausage mode. We still need to analyze this more to extract some other parameters, but as far as we know, was the first observation of sausage mode on this type of very, very small structures in the chromosphere. The next step was to analyze the transverse oscillations of the structures. We basically put one slit in some position along the fibril, and then we record the brightness variation on this, for example, this slit position with time. And then you see how the position of the fibril changes with time. And you see here that he oscillates along the central part of the fibril. And this is a clear indication of kink wave. If memory show you that kink wave is if a magnetic flux tube, you give it a kink, and then he gets perturbed, and then he reacts and starts to oscillate around the central position. And then you see here that this fibril was perturb at some point and then start to oscillate at this fixed position. And this is a strong indication of kink wave mode. And if you repeat the same study, but now for different positions, you see here like 5 different positions along the fibril, and you repeat the same plot, you see that this perturbation is propagating in time. It's not just standing, but also shows some perturbation. We infer all these quantities that I showed here. I resume here. So basically, it's the period of the oscillation. So they show periods are a little bit more than 1 minute. And the transverse displacement is a little bit, it's high, so it goes up to 80 kilometers with a median of 30 kilometers, 35 or so. And the transverse velocities are very, very high. It's around 2 to 5 kilometers per second, and also the phase speed fits in the range of the Alson speed. This type of oscillations, we infer that they have enough energy that what we think is enough to hit the corona and the lower chromosphere, but still we are lacking the dissipation process. So it's not enough to have an oscillation there. It can oscillate and even reduce the intensity, the amplitude by converting to some other modes, but we still need to be sure if you have some dissipation process to dissipate energy to the medium. So one of our future goals is try to understand if this process is there or not. And part of this pass by what we call the non-NLTE inversions. So inversion seeds that I describe here very, very briefly is a way that we can extract the physical quantities of the medium, just looking to the observations. So imagine that you are observing something, and you observe usually the Stokes profiles that I will explain a little bit more into detail on the next slide. So we have our observations, and we think that our atmosphere it shows some variation, some temperature, velocity. So we give this initial atmosphere, and we take it as our initial atmosphere model, and then we compare it with the atomic populations that we think that can be present on this medium, and also the radiation that is present there. And then after we compute this, we compute the possible profiles that this atmosphere will create, and then compare these computed profiles with the observed ones. If they agree, we are fine. We say that, okay, this is our model atmosphere. It's okay. But if they don't agree, you perturb the atmosphere and then repeat the process. This method is used already for several years, but in another assumption, that is the LTE, that is local thermodynamic equilibrium, where you can say that the physical quantities are enough to describe the atomic populations. And for some lines, this is not valid anymore because the radiation also plays a very important role in the statistical equilibrium of the atomic population. So we use with these new inversion codes, we take into account this radiation, and then we try to infer the new populations and departure coefficients from these atomic populations. And this we are also developing in-house in collaboration with some other colleagues, and we think that we may be able to infer the magnetic field topology, because if you analyze if you look just very briefly for how the light reacts to the magnetic field. So here on this panel we have what we call Stokes I, that is purely the intensity that we observe from a filter. But you see here that we call Q, U, and V that describe the linear polarization. These two plots, and this is the V is the circular polarization. Basically, put a linear polarizer or a circular polarizer out in the telescope, and you see how the light changes. And here on the left side, you see the magnetic field vector for some random pixel, and here is how it responds for some average observation. And you see here, depend on the magnetic field intensity and the orientation, you get different Stokes profiles. And this allows us to infer, using these inversion methods, the magnetic field locally for each line and for some formation height. And this is a very preliminary result. Here I just show the Stokes I, so the intensity that allows us to infer mainly temperature, velocity, and some other physical quantities. And you see here the blue line is the orange line is the observed profile, and we have kind of good agreement already for this calcium to H line, that is a non-LTE line, a good agreement between the observations and the fitted line that allow us to extract the physical parameters of the atmosphere. This is what I'm showing here. That is the temperature. This is the log tau. So this is the deepest layers of the atmosphere, and these are the highest one. And you see here, as expected, a decrease in temperature, and then we have more or less the classical minimum of the temperature, and then we have a high increase in temperature here that decrease after. So it can be an observation of the fibril or not, but we still need to analyze it more in detail. If you think that you have a magnetic flux tube that is being heated and then is warm in this very specific location, you assume that we have a very high temperature just locally in height. And we see it more or less here, even though the data is still not completely reduced and it's very noisy. So this is a map of temperature at log tau at 5.5, minus 5.5. And you see here that some of the structures are colder and warmer, but they are kind of diffuse. But if you look here, that correlates with the location at one of the fibrils, you see a very, very warm elongated structure here. And part of our goal is to correlate these warm elongated structures with the bright elongated structures that we see in the intensity images. And also correlate the location of these elongated structures with the velocity. We can infer if this fibril is going up or down, and if you see some correlation between the upflow or downflow of these fibrils and one of these two types of brightness variations that we saw, we may think that, or we may infer how the heating process is being active, or the heating process is there or not, and how they are performing. And I just leave you the summary. So we estimate the morphological properties of these slender calcium to H fibrils. We identify the type of variations. We detect two types of MHD modes, and also their parameters and the energy budget. And the outlook is what we still need to identify the magnetic field structures, and also the formation process and the energy dissipation on them. That's all. Thank you.
Okay, thank you very much, Ricardo. So I think we have time for questions, so we can ask anything from Portugal or Germany or speakers. So if there is any question.
Yeah, so maybe it's a very nice question. How is the strength of the magnetic field compared between the chromosphere and the corona?
Magnetic field decreases. Right.
Decreases?
Decrease. It's smaller there, except in some structures, localized structures. So expect that magnetic field decrease, but if you have some structure that for some reason keeps the magnetic field strong, you have some localized structure like filaments, that is dark regions, but it tends, if you have a magnetic flux tube coming from the photosphere, you will expand with height, and then you expect that the magnetic field decrease.
And what is the magnitude, more or less?
In quiet sun, we have very few, like less than 100 Gauss, and then it will decrease for very few Gauss, and in loops, you can have few thousand Gauss, and then they will decrease to few hundred Gauss.
Or like the layer you study, can you measure that?
We hope so. On this inversion, I still didn't include the magnetic field, but some people did it already from some LTE lines and even for some non-LTE lines, but we still need to check first if our code is able to retrieve this information. In principle, yes, but it's too early to be sure. But it's totally worth it to investigate.
So, any other question?
Thank you, Ricardo, for a very comprehensive view of your work on the topic of fibrils. And it is certainly the first steps to understanding what's going on in the chromosphere, and we need some more observations. But I am glad that you are embarking on inversions and on deducing physical parameters from the profiles. And I wonder how you interpret the profile of line of sight velocities you've been finding right there, since it seems that you have blue shifts in one part and red shifts on others, varying with height. So what does this mean?
First, I just invert calcium to H data, so it's sensitive just a small fraction of the height. But I tried some other inversion with H and K to try to constrain it more. And actually, I was hoping to see these variations in redshift and blue shift in height. If I have some local, if I have a fibril that is moving up and down, I don't expect that the full atmosphere will react at the same time. So it depends on the time scale, but that's I need to analyze the evolution of it. So I have also the time variation of this. So I saw in some profile, this one is quite well behaved.
These are 1D inversions.
Yes.
So time shouldn't be, so you are averaging in time. So your dynamical view that doesn't fit.
Between redshift and blue shift in height, if they vary or not. Because if I imagine that is my magnetic flux tube that is reacting to some other perturbation, I don't expect at this moment the deepest layers, but for this I need more lines, of course. Yeah, I need more lines. That I don't expect that the other layers will react at the same time for this velocity. That can be interpretation, but it will be difficult, it's true.
So any question? No? So if not, I have the last question. So because usual as a technique just to detect these small fibrils in chromospheric data, and I wonder if you can apply the same techniques to other structures, for example, to trace the evolution of spicules or anything. So it is, you can apply that directly to other kind of structures.
On sharp mask, so basically we have a kernel that we convolve that will extract the range of width that you can also play with it, and then you just need to fine tune it in a way to the data. So we will be blind to very, very large structures, but if you tune this kernel to the structures, the range of structures that you want, it should perform in the same way.
Okay, thank you. So if there is no more questions, I think I just close the seminar, I guess. And I thank the speaker.